In the last step, we generated the mesh, and in this step, we will set up the case for simulation. And let's follow this procedure, although there are different orders we can do, but let's do this procedure. First of all, we set up the physics in here. So basically, we set up the algorithms and the turbulence models. Okay, so we can open physics 1, double-click models, and you can see here, three-dimensional is already pre-selected for us. We use steady, so we are simulating a steady flow. And since it's air, so we choose gas. And we will use segregated flow. And for now, we are simulating at 100 mile per hour, the speed. So the wind is coming from the inlet as 100 mile per hour. And in that speed, it's about 50 meter per second. So the compressibility effect is not very significant. So we choose constant density. And we will choose turbulent flow. And this time we choose K omega model. And you can see here, the transition model is optional. We just keep it free. And the optional models in this box, we keep it free. Then we close. Okay, so now we set up the models, and we can have a check of the reference value. And you can see the pressure reference is this, and initial conditions. Okay, because the difference to reference is 0, the pressure initial condition, and we only need to change the velocity. Okay, so we know it's 100 mile per hour from the inlet. Notice here the positive x is towards the right, and the flow is coming from right to left. So we need to have x velocity is minus 100. And also we need to change the speed, mile per hour. Okay. In STAR-CCM, we can just use mile per hour as a unit also. Okay. And this is the initial condition. And now we need to change the boundary condition. We go to regions. The boundary condition can only be set up once we have the models. That's the order why we go through this order. Boundaries. And okay, so let's just go through area 1. The first is subtract color phase 1. So that's basically boundary, the surface of the half front wing, and its wall, no problem. And let's see exterior. So this is exterior. And this time, because this is sufficient far away from the model, usually we set it as, if we come to here, as wall, that's correct. But this time we want to do something different. And if we go to shear stress specification, usually for wall, we use non-slip boundary condition, which means the velocity at the wall is 0. But this time we use slip condition, which means the velocity is like the free stream. Okay, so there's no boundary layer. It also saves us time in the calculation. Okay, and let me move the plot. So that's the difference we do. We change it to slip wall. And the floor, that's wall, no problem. Inlet. Okay, inlet, we need to change it to velocity inlet. And if we open it, and flow direction is normal to the boundary and into it. So we need to change the velocity magnitude to 100 mile per hour. Okay, so this is boundary condition. We don't need to worry about the orientation because the inlet is this way. So anyway, it will be this magnitude. Outlet, we will change it to pressure outlet. And symmetry plane, of course, we want to change it to symmetry plane. So this basically is a boundary conditions we have. This is second step. Now we go to the third step. What's the third step? The third step is to generate some monitors to report the force, because it's front wing. As I introduced at beginning, we are looking at its downward force, and a drag. So we need to generate some reports. So we go to reports, right click, new report, flow energy, and we choose force. Okay. And first of all, we will define downforce. And it doesn't know whether it is downforce or drag, so it's based on the direction. Okay, so downforce is going down, so it's -1. Y is -1, but X is 0. Okay, this is become downwards. The fourth option, we choose both pressure force and shear force, and because it's a non-slip boundary condition, right? And more importantly, we need to choose the parts where the downforce will be calculated. We go to region, that color phase 1, which is the surface of the front wing. Then we set the reference pressure as the reference pressure in the initial condition. Okay. The next is the drag. We don't need to set up new one. We just copy and go to report, right click, and paste. So we change it to drag. This is a drag. And the drag, different from the downforce. It's along X direction, but in here it's along -X, right? So we have -1 and a 1, but Y is 0. So this is a drag. Okay, then we select both by control and create monitor and plot from report. This allows us to see the progress, and we plot them in the same plot, so single plot. And you can see one is downforce, one is a drag. And okay, so while we are doing the simulation, we want to see the progress of the flow. We can see the flow, and for example, in the derived plane we have. And now I'm generating a scalar. So this is scalar we have. Let's move to the scene plot. So we have the scalar. And so the scalar, we want to attach it to the surface. So which part is it? We need to click part and choose the derived parts, the plane section. We can monitor here. So this is a plane. And let's move the orientation. It then makes better understanding view. So positive, -X. Okay, so this is not good. So basically, you want to view it this way, right? Let me see, how can I change orientation? And Y top, no. Z, Y up. Seems very hard. Let's just keep it like this. And also we need to set the function which scalar we want to visualize. This time I want to visualize velocity and X component. So we go to laboratory I, so that's X component. And now we are nearly done. So the fourth step is to initialize the domain. Click the green button. And we will wait a little bit this time because it's a 3D simulation, a lot of grid. And you can see the plane is now highlighted as yellow. That's initialization. So 100 mile per hour is equivalent to 45 meter per second. In the next step, we will see the result and start the simulation. We've set up all the requirements, all the parameters for the case. So now what we can do is to run the simulation by clicking the running person. And you can see the residue, how it progresses. And because it's 3D simulation with a relatively large domain, and it takes a while to start. And you can see now we finished the first step. For now, this simulation might take a few hours to finish. And so we can see the residues start to develop. And in the course, we can change the visualization in here. If we go to scalar and click scalar 1, which is x velocity, and we choose smooth. So the contour will show up in a better way, smoother. It's a bit more mosaic now, but we can change it to a smooth one. Takes a bit longer to respond. Okay, so we will keep it running, and yeah, you see this is smooth contour. So most of the speed is negative. Negative means the flow is coming this way. And if it's positive, means there is flow separation, which is not desired. Okay, so now let's just keep it running, and we will see the results later. Okay.